Aloha and welcome to week 9, where we get into waves and tides. So, today we're going to explore just waves. The One of the most visible things that I think we see in the ocean. Even if you've never really thought about the physics behind waves, you've definitely experienced them. And our goal is to understand what a wave is, how it forms, and the basic anatomy of a wave. So, looking at the parts to a wave, and that'll be a foundation that will help us as we look more into um, tides and how waves work later on this week. So, what is a wave? It's important, super important, to understand that a wave moves energy, not water mass. So, a wave is energy moving through the water, not the actual water moving forward. Water particles move in a circular orbit, but the water itself stays essentially in the same place. We'll look at a couple diagrams of that as we go on. But it's why when you see like a cork in the ocean, it'll mostly bob around in kind of the same place for a long time. It's what traveling across the ocean, energy is transferred from the wind. That distinction will become more important as we talk about tsunamis at the end of this week. So, just really important to think about that energy is transferred, not water mass, as waves move. We're going to look at a diagram of all of this anatomy here in a minute, but understanding the anatomy will help us understand wave behavior as well. So the crest is going to be the high point of a wave, the trough will be the low point of a wave. The wavelength is the distance between wave crests, so essentially the length of one entire wave. The wave height is the difference between the crest and the trough. The wave period is the time it takes for two crests to pass the same point. So essentially one wavelength to pass an entire point. And that's important for wave power. So when we talk about the speed of a wave, we call it celerity because we can't talk about speed because the water's not actually moving. It's just energy moving. So that's something we'll talk about a little bit more later as well. And then the wave base is 1/2 the wavelength. So from trough to crest. And that's going to be important when we look at shallow water waves a little bit later. So here are all those things and a couple others. The still water line is just kind of the base of the water. The crest here at the top, trough at the bottom. Water depth is going to be the bottom to the still water line. Wave height is from crest to trough. Amplitude is essentially half of the wave height, and that's essentially from the still water line to the top of the crest. Wavelength, you can measure it from trough to trough or from crest to crest. Either one should be the same, and either way is a reasonable way to measure that wavelength. I think that's it from this slide. This will be a great one to use to study, to remember all of your definitions of the wave anatomy. So, how does wind generate waves? Wind waves are created essentially through friction between wind and the ocean's surface. The size of a wave depends on wind speed. Stronger wind is going to transfer more energy. Wind duration, the amount of time, like if the wind only blows for half a second, it's not going to be enough to actually make waves. So, the duration of the wind. And then fetch is essentially the distance the wind blows across open water. So the more distance that the wind is blowing, the stronger it's going to be, the bigger the fetch and the bigger the waves. So stronger, longer wind equals bigger waves, more fetch also equals bigger waves. And now we're going to talk just a bit about deep water waves. If the water depth is more than 1/2 of the wavelength, then deep water waves move through the water, and it means that the wave doesn't feel the ocean floor at all. The circular orbit will not be changed. So they're going to have complete circular motion. They have no or very, very little interaction with the seafloor at all. And those longer waves are going to travel faster than shorter waves. So that's going to kind of set up the process that will lead to swell as well. And here you can see we have deep water waves, and they either don't or barely feel the seafloor. Okay, no motion of water on the seabed due to passing waves. So that means that this is a deep water wave and it's not being affected by the seafloor at all. This one is just starting to be affected by the seafloor, but it's still, the depth to the wave base is still just over 1/2 of the wavelength. And so it's still considered a deep water wave, but it is transitioning into a shallow water wave here, because that can either happen because the ocean floor is getting shallower or the waves are getting longer. Either way can make that equation come out. Now, wave dispersal and swell. Dispersion is the natural sorting of waves by wavelength. So if a storm generates all kinds of waves, the longer period waves are going to travel faster and essentially come together into a swell to make one big wave. When that swell reaches like Hawaii, we see big, clean, evenly spaced wave sets that can travel many, many miles from their origin. Sometimes they can travel thousands of miles. So Pacific storms send big swells to Hawaii. I'm sure most of you have seen on big swell days. And if you've ever swum in it, it's interesting. When we have a windy day, we'll get choppy waves that are tiny and difficult to swim in because they're one after the other and they're small, but they make it hard to breathe. When we get big swell, it feels like swimming on an elevator or a roller coaster. You go way up and way down, but it doesn't really affect when you turn your head to breathe because those waves are so big that you're essentially swimming on the top of them and then on the bottom of them. So for me personally, it's really fun to swim in a really big swell day, as long as you're far enough out that it's safe. And it's less fun to swim in a shorter wavelength day where the waves feel choppier. So what controls wave speed or celerity? So calling it wave speed is maybe not the right term. I should probably have put celerity in here. But in deep water, wave speed is determined only by wavelength and period. Longer waves, meaning longer periods, travel faster. And that's why a long period swell can feel very, very powerful, even if it's not very tall. And then in contrast, those short, choppy waves feel more chaotic, which is what makes it more difficult to swim in those choppy, short period waves. And you probably, if you surf or spend any time in the water, you probably feel that yourself too. And I'd love to hear examples of that in discussions or in office hours. Okay, real world examples. So Hawaii has some of the best examples of big organized swells in the world. We get those big, powerful waves generated from storms many, many miles away, and they have really long fetch, long periods, and high energy. And that's part of why people love to surf off the North Shore of Oahu. It's got some of the biggest, most powerful waves in the world. And people who come from other places to surf there are appalled by the big waves, and it's wild. And the North Atlantic is going to have much shorter, steeper, and more chaotic waves because the fetch is much smaller. It's generally limited to storms that change really quickly and just aren't as big and powerful as the storms in the Pacific. So this comparison really shows how the basin size, the Atlantic basin size versus the Pacific basin size, can affect the fetch, which then affects the wave energy. So the Atlantic is much smaller, and even a very big storm in the Atlantic just isn't going to have the distance over time, the fetch, that we can get in the Pacific. So now, why does this matter? Well, it helps us to interpret surf forecasts. It helps us to navigate safely in different places. It can help us predict coastal erosion patterns. It can help us to just understand all of what's going on in our oceans. And again, the oceans are major economic tourist attractions, And all of that matters for safety and swimming and surfing, all those things that we enjoy doing in the ocean. And this is going to be some of the foundation for lecture 2 on wave transformation and how waves change. So lecture 2 is going to be about what happens when waves reach shallow water. So shoaling, breaking, refraction, and energy focus will be our focus for lecture 2 here.